Mihaly is one of the PIs for the current NLSI teams, and we're very pleased to have him present this talk today, which he has entitled Expectations for the Lunar Dust Experiment, LDEX, aboard the Lunar Atmosphere and Dust Environment Explorer mission, LADEE. Please take it away, Mihaly.
Yvonne, thank you. Thank you very much. I would like to start by acknowledging the team that is listed at the bottom. It's an incredibly hardworking and very reliable set of colleagues. Without them, this instrument would not be ready to fly. Let me start by advancing the slide, if I can. Here it is. Why do we anticipate a dust cloud around the moon? First of all, it is bombarded by interplanetary dust at all times, and that generates secondary ejecta that will produce a permanently present dust exosphere. This sounds almost obvious, but I have to tell you that the first time it was recognized was 2002. That was the first time a dust detector flew by an airless object at a close distance, and we could find this dust halo. That was Galileo at Jupiter, and the object was Europa, an icy satellite. Since then, we have seen these dust clouds at all the Jovian satellites. We have indications at the satellites of Saturn, but actually it was never measured or identified around our own moon. We know about these dust halos at other places, much more details than what we know about this in our neighborhood. In addition to the continual bombardment, of course, we expect time to time to have really high densities of incoming particles due to meteor showers, and hopefully we'll catch some of that during LADEE. In addition, we also believe that due to solar wind and UV charging, especially at the terminators where large electric fields can develop, we can possibly see lofted dust particles. But the only indication of that is very vague, and actually it is from images taken by the Apollo astronauts looking towards the sun, seeing extra brightness. So this is kind of a summary of our models and the kind of the observation by, or the visual and the imaging taken by the Apollo astronauts. The one single dot at a density of 100 at an altitude of 50 kilometers above the lunar surface is the only indication that there is dust, and the red indicates the model that is kind of the combination of impact ejecta and lofted particles. So there is a big discrepancy. We are very curious to see what we're going to find. Based on what we know or what we expect, we could put together an impact rate for an arbitrary dust instrument that has at least 100 square centimeter sensitive area. And the top plot shows you the density. The color there is density. These big color ears are the small particle population that we expect to be present at the terminators. And it's kind of hard to see, but there is a gradual weakening of big particle densities that is due to the impact ejecta. I can turn that into impact rates. This is, again, for the same orbit, which was a 30 by 100 kilometer orbit above the surface. And I expect then an impact rate for big particles that is a few per second in general, all around the orbit. And in the morning and in the evening terminators, I expect these huge intensity enhancements of tiny dust particles. The most sensitive dust detector that we can build so far has to do with impact produced plasma detection, and that is a high-speed particle would fly in and hit a target, make a plasma cloud that is consisting of electrons and ions. An electric field is set up such that the electrons are recollected on the target, and the ions are sucked into a multi-channel plate, giving you a highly enhanced signal. The impact charge that we expect as a function of speed, actually what I'm plotting here is charge over mass and speed, would tell you that it is very hard to detect small particles. Particles that are much smaller than a micron, there is insufficient charge to be detected. So what then you could do instead is do a trick in a sense that the electrons are all collected to the target. The ions are collected into the multi-channel plate, but that signal is split into two. For big particles, that the signal is big enough to be over a threshold and can be detected individually. We do single particle detection. And we also channel some of that signal into an integrator circuitry that would measure the little impacts, the integrated signal due to the little impacts that are too small to be detected one at a time. The way it is going to work is here. This is a big impact. The particle comes in, and this is the signal on the target. And that's the time versus the impact amplitude. Notice that at the accelerator where we test these devices, which is, you will hear a talk in a couple of minutes, here at Colorado, we built a dust accelerator, and this was, LDEX was our first flight instrument customer. The charges are very high. So you will notice as the particle approaches the target, there is an impact charge induced. In space, the charges are much smaller, but for big enough particle, LDEX will be able to measure the charge that the dust particle carries in space, which is a really difficult measurement. Cassini couldn't do that until it went much further away from the Earth. So that's very exciting. This big, beautiful booming signal then is the multi-channel plate. This was a particle that was slightly bigger than a micron in radius, coming into the instrument slightly shy of 2 kilometers per sec. In addition to single impacts, then we are ready to make measurements of multiple impacts. This is actually still for single impacts. I'll show you that we will deliver what we promised, and we are capable of measuring much smaller than 1 micron size particles as in a single impact mode. And for the integrator mode, on the left, I'll show you the instrument when there is only UV is shining. And then what happens is we turned on an ion signal that is comparable to the to the signal that a lot of small particles will generate. And every 1 second out of 10, we make the instrument blind to dust, and we recover the signal that is due to everything else but dust. So the instrument is self-calibrating, and along the way, it will be capable of subtracting all the background and identifying the signal due to small particles, the collective signal due to small particles. This is what I expect. We will see. This is 6 minutes out from crossing the morning terminator. This big forest of signals are big particles. They will be detected one at a time. They can be subtracted from the integrated signal. And what is left behind is proof that submicron sized particles exist lofted over the terminators. We are busy working on tools. The mission is short, and we have to be very quick on our feet to do the best analysis in a very short amount of time to come up with the optimum settings for this instrument. This is just a snapshot. By now we have the orbits, what we expect for LADEE. We can run that through our model and make a predictive tool that, depending on which phase on orbit you are, how much dust particles you expect to see as a function of their size. And as we go on, this will be used as a tool to visualize the amount of particles that we measured in orbit. The next set of tools is we have full waveforms coming down for most of our impacts, and every single event can then be identified as noise or real, and we can tell you about the mass, the speed, and sometimes even the charge of the impacting particles. So this is a list of all the contractual needs or requirements that we need to deliver to NASA, and I am happy to tell you that for single grain detection as well as for the collective signal detection, there is a green check mark everywhere. We will measure, we are ready to measure everything that we promised this instrument will be capable of doing. Finally, this is an image that was taken, just a month ago or so. This is at Wallops. This is the top of the LADEE spacecraft. You see our instrument. This is the last time the cover was opened. This is the last cover testing. It's going to be, it has been closed 30 seconds after this image was taken. Everything is working fine. After this event, we only had to install one more little plug that the instrument is safe to arm, safe to turn on the high voltages. These red pipes that are there to keep the target clean will be removed, and LDEX is good to go. Thank you.
Thank you very much. Wonderful. And Mihai, it looks like we already have one question that has been typed in for you. And it is, what is the largest size of lunar dust that may levitate from the moon's surface due to the solar-based radiation?
Okay, surprisingly small, probably 10 nanometer.
Okay. Interesting. And I was wondering, I know that LDEX is designed to look at the atmosphere, the 30 to 100 kilometer region, but is there anything about the surface that these observations might actually tell you as well?
Oh, absolutely. So if we map out the size, how much dust we measure as a function of size and height, we will tell you how the surface responds to the incoming dust. So we could tell you something about the porosity, something about the distribution of the ejecta velocities and sizes, angular distribution and speed distribution. So that would give us a lot of knowledge about the mechanical state of the surface. That is not a direct measurement, so the best next step would be to make dust measurements on the surface. But as we gather these pieces of information from orbit, we should be able to come up with a much better set of questions and ideas what to measure once we get to the surface.
Great. And Micah Scheibel would like to know, what is the contribution from micrometeorites that you expect?
Okay. So believe it or not, the amount of dust that hits the Earth, we don't really have a good handle on it. It is somewhere between 50 and 150 tons a day. So if I scale that to the moon, the incoming stuff is on the order of 5 to 15 tons of material a day, and the yield, the response to every gram of incoming particle could be 100 or 1,000-fold. So there is a whole lot of dust being generated as secondary particles. Of course, depending on their speed distribution, they will reach different heights. So depending where you are at and what size particle you are looking at, that contribution will be very variable. Also, we expect the plasma effects or the electric field effects to be efficient at the terminators. So it is possible that at the low pass, at the terminator region will be dominated by plasma lofted particles, and then the rest of the trajectory will be dominated by ejecta grains. In general, I expect, because of the physics, how levitation, I think, would work, that if any particle bigger than half a micron and even 0.3 micron in radius is probably an ejecta particle, not a lofted particle.
Okay, great. Let's see, we have another question now from David. It says, Mihai, you may have mentioned it. For the 10 micron grains, does LDEX have the sensitivity limit to see your best guess exosphere of 0.01 cubic centimeters at 10 kilometers?
For the, I believe so. In fact, the limitation, the challenge is to have single impact detection. And that we push down to the best of our ability, that will be around 0.3 micron in radius. Those will be detected one at a time, and all particles below that we will notice. If you are asking what is the background, kind of the dark current, how little dust can hide from us, I think we should be able to do as small as maybe 1,000 particles per cc. If they are there, we should see them.
Okay, great. Thank you very much. And if there